Good afternoon, Jan.
Michael, I made it. I made it.
Ah, excellent.
No, got. Sometimes if somebody else makes an appointment for you, then things get complicated. But especially, especially if it's my wife. Um,
hmm Yeah,
yeah.
but she knows that this time is precious, right? So, yeah,
Yeah, she knows. I told her 1 hour ago. She called me. She said, "Jan, somebody will bring you some bread. Somebody I know, and then you can just eat together before you have your meeting."
Okay.
and
Well,
that
that.
somebody to, and that somebody didn't know she was supposed to eat here. So
Ah, okay.
she turned up 2 minutes ago. I say, okay, forget it.
Hmm.
Uh, okay, will be
Uh,
another time.
yeah, yeah, but that sounds like the kind of meeting that you definitely want to take some time for. Just get to
No, not special.
hang out
Just
with
just to
folks.
eat.
Okay.
Okay.
Well, good. So yeah, I had some progress over the weekend. So
Hmm.
I wanted to share some of the things that I'd updated about the result composer. And in fact,
Okay.
I think when as we've been talking about SQL, yeah, I basically stopped at the result composer and said, okay, now that you've got these results, yeah, this thing puts it together. The end.
Yeah.
So yeah, as I was working on the replicator as a service, an issue popped up, and I said, "Oh, I need to fix that right there." And then I realized that that would be a change to something that is directly um, within your view. So so hopefully that change doesn't affect any of the things that you've been looking at or working
Mm.
on. But
Well,
yeah.
let's see how it goes. Now, this week, I was supposed to work on that automatic SMS sending and receiving
Yeah.
from the Google Sheets. But then they said no, the synchronization. So I got already by scraping fill up the Google Sheet.
Uh huh.
But then when they change something in the software, I have to scrape again and to synchronize the Google Sheet.
Mm.
So that got priority. So that's working now.
Ah,
But
good.
then you say the synchronization is is difficult.
Yes, it is. That is one of those hard
Uh,
problems.
and then I think about historical modeling where you just send immutable things.
Uh huh.
Um, no, but then you have in your spreadsheet you have messages, but the synchronization will just override them.
Mm-hmm.
But you still need the old messages, so
Mm.
you write them behind in a note in the cell.
Mm.
Um, but of course, the next one you synchronize, you have to keep the history
Yeah.
um, and all these little things.
Yeah. Yeah. And you only have one place to store a note. You can't. The
Mm.
next one's going to overwrite that. So yeah.
Spreadsheets are not made for programming,
Mm. No.
but it does work. It does work.
Yeah.
Um,
Yeah. And so much of our societies run off of spreadsheets that
mhm.
yeah, it's um, it's so uncanny that so much of this works that it makes me think, okay, there's something more to it than this was
Mhm.
just a convenient way to think about the problem. There's some other nugget there to capture.
Mhm.
So yeah, hopefully, yeah, as we make our way back around and make make Janaga replicators more and more accessible, we can get to the point where the people who would be solving problems with spreadsheets would look to a replicator instead. I don't know what that world looks like yet, but
Or connect their spreadsheet directly to a replicator
mm-hmm.
instead of storing and using the spreadsheet as a user interface.
Yeah, 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 I can see that.
I don't know. I don't know
Uh-huh.
because now I'm actually storing the data in the spreadsheet,
Mm-hmm.
and I have this synchronization problem. But you might as well the scraping do it directly to a replicator,
Mm-hmm.
out of the scraping generate facts, put them in a replicator, and use the Excel spreadsheet as a front end, where, but then you have to interpret the facts.
Yeah.
And everything you do generates a fact which goes back to the. Well, let's see where we get.
Yeah. Yeah, I'm already trying to solution that in my head now.
Just a crazy idea, but who knows?
Yeah. All right. So let me go ahead and share with you where we are on the Postgres store in Janaga.js. So the things that let's see. Looks like I've. Oh, that is weird. Okay. It looks like Discord has made a change, and now when you transition away from Discord, you can no longer see the videos. Let me real quick just try something, see if this is going to work. This is this is going to be really weird if it actually does work, but okay. Yeah, that's kind of working. All right. Yeah, you'll see on the stream when you watch it back that it's not perfect, but
I see the code. That's
yeah. Yeah. All right. We'll make that work, and then we'll come back and try to redo the recording setup so that we've got a solution. Okay. All right. So what we're looking at here is the Postgres store in Janaga.js, and then the other thing that I want to take a look at, we'll look at distribution rules later, is the specification result SQL. So this is the thing that generates the SQL, and also contains the result composer. So right here's the result composer. So that's going to be something really important. So how these things work together is the read endpoint for Postgres store, for any of the stores really, will take a list of references. These are the givens, and a specification. And so we talked about the structure of specifications. So part of specification is that it has the yeah, I thought this was doing the check against the specification given, but yeah, the specification has a set of given labels, where a label is just a name and a type. So so yeah, I was expecting to see some code here that says, oh, I have to make sure that I've got the same number of starts references as I do labels in the specification given, and the types have to agree.
Yeah, I do remember that code somewhere. I've seen it somewhere.
Yeah, so it might be that I implemented that in the in-memory store, but didn't implement it here.
Perhaps.
Yeah.
Perhaps.
But at any rate, it's going to generate some SQL from that specification, and at the same time put together a result composer. So the result composer knows what the SQL is for each of the different queries it's going to run, and it knows how it's going to put those results back together in order to give you a full projection. And so now we can get the actual SQL queries from the composer, and then open a connection and execute those SQL queries. So for a very simple specification, this just ends up being one SQL query. But for a complicated one, then it's going to have an additional SQL query for um, each child projection. So
Yeah.
so yeah, you select a list of courses, and then for each course you select the list of names, and then the list of instructors and that kind of thing. So it says, okay, here's the course query, here's the names query for all courses, here's the instructors query for all courses. So you've got those three, and then you compose them together.
Yeah. For the day where I arrived, I had for a simple query, I had just one SQL query, and then I had to execute it. And there I was working on in the connection factory.
Okay, good. So that means you're not quite to the point where these changes that I just made are going to affect
No,
anything you've already done.
no, the composer is is the next step, I think.
Okay,
So this comes very well.
good, good. So then the parts that I changed are these things right here. So the first thing is now that we've executed those queries, we've got the result sets, and now we're going to find all of the fact references inside of those result sets. So this is everywhere that you have selected the fact itself. We just want to pull out that fact reference. Yeah.
And that result set, what is the structure of this result set?
Yeah, let's dive into that. So the result set is a result set tree. So if I go here, we can see result set tree. Okay, so so it's an array of rows, and then the child result sets, and these are named result sets, so they have a name in addition to all of this stuff. So that's what makes it a tree. So so just focusing on the child result sets with that course example, the top result set tree wouldn't have a name. It would just give you the courses, but then you've got course titles. So then there would be a child result set tree with the name course titles, because that's what you used in the projection to name that child, and then that would have its own set of result set rows and its own children. So you can go down the tree as deep as you need to.
Yeah. And then that result set row, that's a fact index.
Yes. So
And
yeah. So it's a map, a dictionary from fact index to result set fact. So
you adjusted
yeah
the hash, the fact ID, and the data. Okay.
Yeah. Yeah. So the fact index, as you generate the SQL, you allocate fact indexes. So starting at 1. So when it selects from the fact table, it gives that an alias: F1, F2, F3.
Yeah.
So so this way we know for for that particular fact index, this is the information that we got back from the select for that particular fact. So here was the fact ID, which is the ID that's just in this database. It's not a universally honored ID. And then the hash, and then the data, where the data is a JSON object that has fields and predecessors.
Mm-hmm.
So fields are just name value, and then the predecessors are either a single fact reference or an array of fact references. By role. So it's a lookup of for this role, here's this one fact reference, or here are the array of fact references.
Yeah.
So that's basically the JSON structure that's coming out of the database. So basically, you run each of the queries, and then each row in the query becomes a result set row, and then you take those 3 queries in this case, and you put them together so that your top query has the 2 as child result sets. And you just say, there's the whole result set tree. So that's what comes back from here. All right, so then the next step is to go through those result sets, looking at the so it's the composer that's doing this, and so the composer has the specification. So it's using the projections in that specification to figure out, okay, at this point you are trying to project an actual fact, as opposed to a field or a hash or or a collection of children. Mm-hmm. So when you're trying to project an actual hash or an actual fact, then it pulls out the fact reference from that result set. So now you get all of the fact references in that entire tree of result sets that are going to be projected. And then you call this existing method, load. This was already here for the server to be able to, after you've fetched a set of feeds, then the client says, all right, these are the fact references I know about, and these are the ones I don't. So take all the ones that I don't know about yet and ask the server to please give me the fully realized graph from these fact references.
Yeah.
And so this one goes through the where was that? It goes, there it is, the ancestor table. So it's using the ancestor table in order to say, I want this complete transitive closure of all of the predecessors, and then selects them down to the actual data from each one of those, and gets those things and merges them all into this. This is the map of fact types, but topological sorter is the thing that's putting all of those fields, all of those facts into a list of records that are from the top down. So the very first record has no predecessors, but then the second one could have the first one as a predecessor, and so on. If a record is written, its predecessors have already been written, so you've got that full graph.
Michael, but here we are on the server. Does that mean the server gets a query that it will send the full graph each time?
Yes. Let me see if I happen to have such a thing already loaded up in Postman. Okay. So let's go to replicators. And
then we have
right here.
Because we have the bookmarks.
So we start by looking for the feeds. You know what? I think this one's going after dev.janaga.com. So this one might actually have good stuff. Oh, I have to be authorized. Let me go ahead and I don't have authorization set up. How did I have this working? Okay, anyway, let's just kind of walk through the queries. I can probably start a Docker container to satisfy this set of queries. But so it starts with, here's the entire specification that I want to run. Give me the feeds, and then that gives you back the list of feeds, and then you can use get with that feed ID and a bookmark, so the question B, and it starts off as blank in order to get back the list of fact references. Yeah. And then you pass those references into load, just the ones that you don't yet know about. And this is what returns the fully realized graph of facts. So it loads all of the fields and the predecessor references for the entire transitive closure.
Yeah, but I find it bizarre. So we use a bookmark just to get the new facts or the fact references, and then when we use that fact reference to retrieve that fact, then we are going to retrieve the whole history.
Yeah.
Well, we should just retrieve the fact itself, no?
Yeah, there is an opportunity for an optimization. So yeah, we can actually look at this in.
Am I missing something?
Let's see. You should be seeing the. You should be seeing a browser where I'm signing in using GitHub.
Yeah.
Okay. Yeah. So I'm getting signed into dev.janaka.com so that. Let's see. Start GitHub and approve the sign in. And
yeah, being redirected.
Okay, excellent. All right. So now let's take a look at our network, and we can see that that nice little waterfall happening. Okay, we missed the first half of it, so let me refresh that. Okay, yeah. So yeah, we did the the feeds, got back the list of feed IDs, and then for each feed ID, we do this thing where we're getting from the feed endpoint, starting with an empty bookmark, getting back just the references.
Mm-hmm.
And then we get to a point where now we've got a set of references, some of which we don't know about. And I say, okay, these are, let's see, right here's the payload. Yeah, here's just this one fact reference that I don't know about, and it's trying to do a load. So this one's nice and easy to look at. So we've got the type and the hash. So here we're starting with the username, and so in order to fully realize this, we need to know the user as well as the username, all of the predecessors and the fields associated with both of those facts. And so it sends back the user and the username. So these being the hashes, the predecessors. The user itself does not have any predecessors, but this one has the user being that particular reference, and then the fields that go along with them. So the public key here, or the value of the name here.
Mm-hmm. For example, for that user fact that we are getting back,
mm-hmm.
didn't we already have it in the local database?
Yes, yes, we did, and that's because that came back from the login. So you are correct. So it computes the transitive closure because it doesn't. You've already filtered out the ones that you know about, and you're giving it the references that you don't know about. So therefore, the server doesn't actually know that you know. You've already filtered out the Janaga user reference, and so when you ask the server for the username, the server doesn't know you already know about the user, and so it includes that in the tree. So yeah, there is an opportunity for some optimization there.
So imagine I have two devices which are communicating with the same replicator, and on one device I keep changing my name, so I keep changing the username.
Mm-hmm.
Every time there is a new name fact which goes to the replicator, and my second device has a feed on the username. So every time I change my name here, my second device will get a notification,
Mm-hmm.
will get that feed with the bookmark, so we'll just get the latest name fact, and we'll then go to the replicator to load the name fact. But every time I will get the full history of names back.
Yes,
Is
that is
that correct?
correct. Yes.
Okay.
Yep, and that's because each name has as its predecessor the prior one. So yep, you are going to be getting that full graph, the entire chain.
Okay.
And yeah, so there's an opportunity to optimize in a couple of ways. So first of all, what I don't want is for the server to have to keep client-specific information. So the server shouldn't have to remember what the client already knows. That impacts scalability. This way, it gets to be a stateless protocol. So that optimization path is ruled out. Otherwise, we could just have the server remember, oh, I've already sent this to you. Let me not send it to you again. Another option is that load in its payload could also send, and these are the references that I already know about. So that could be, of course, you don't want to send the entire database. Here's my entire client database, but I think that there's some way that we could say, I know that these references came from this particular feed, so the shape of the query looks like this. The specification looks like this, and so therefore I'm going to send you the references that match this specification, or at least part of it, that are in those tuples somehow, that that I already do know about. It might actually be correct to, after you've received these fact references here. So like in this case, the replicator is part of the tuples that you get back. So it might be, oh, I already know about this, I just don't know about that. So therefore, I'm just going to filter out. These are the ones that I do know about. These are the ones that I don't know about. That might be sufficient. And even if it's not sufficient, it's still correct. There's nothing incorrect about that.
Would it be a solution if you just, when you do a load, that you just get the fact that you asked for and not all the predecessors?
Yeah, the problem there is that, if that fact has another predecessor, it's going up a different part of the graph that you don't know about, then you would have to say, oh, I don't know about that one. Let me get that one, and then you get back its predecessors, and you would just keep on going up the chain. So you'd have a lot of round trips.
Yeah. So the optimization could be, if we are sure that we have all the predecessors, that we do a load with a flag, don't give me the predecessors. And if we are not sure, if we are not sure, then we load everything.
Yeah, there's no way for the client to be sure because it doesn't know what the predecessors of these unknown facts are. But yeah, if it includes the ones from this set that it does know about, then at the very least those can be used as kind of stops as it goes up the graph. So it says, okay, I know you know about this one, therefore you know about all of its predecessors. And so I'll stop traversing the history at that point. And so that way, if the feeds do include the immediate predecessor of the name, let's go to the one that's got the user. So we're talking about that specific scenario. So if this feed gave you the username plus its immediate predecessor username. And then you can say, oh, I already know about that previous one. Here's a reference that I don't know about, so I'm going to give you those two things. And then the server can say, all right, I'm going to start going up the chain, and then as soon as I get to a reference that is in your known set, then I can stop going up the chain. And so in this case, it would be able to give you back just the username that you don't know about.
Okay.
Although in this case, well, yeah, this is in this case, yeah, that's not quite. I mean, that would still be a correct optimization, but it can do better because the user is not coming back in this particular feed. It wasn't part of the the results. Okay, but yeah, if you included the givens, then it could be better. Okay, yeah, so I think there is a way through this. I think it can be optimized.
Let's solve it when it becomes a problem.
Yeah, I like that.
Last time you said, let's make it a problem.
Yep, let's make it a problem.
Let's solve it when it becomes a problem.
Yeah, exactly. So yeah, so that means for the purpose of today's discussion, we've got this this operation that we can perform on the store that says, given a set of fact references, a list of fact references, give me back a list of facts that are in topological order.
Okay.
And that is what this this method is doing. So that's why we've got our topological sorter there. And that gives us, right here, all of the fact references for those particular, or those that gives us all the fact records for those particular references and their predecessors. So this is enough information to put those facts together. Yep, and these were the facts that you're directly projecting. And then you give that set of records to the composer, and you have it do its work. So, that was the new part. What the composer was doing before with a fact projection is just giving you the fields, which was useful in the /read endpoint, so that you could just see. I just want to select this fact, and now you could just see the fields of it, and you could continue to refine your projection. But yeah, when I got to actually running the read function on the server in response to a j.watch or j.query, then I was getting back just this set of fields rather than a full fact, and I needed the fact for the code.
Okay, so this compose. Here we are in the read method.
Yes.
Okay. And so what was the return of that method?
Yeah, so this returns, and actually this has changed to a projected result. It used to just return an any array, but now projected results has the actual result, that's the any part, but then it also includes the tuple for this particular result. So that's the named fact reference. So now this comes right back to the specification as it was originally designed, not as it was interpreted in SQL. So you've got these names, and then the particular fact reference that goes along with those names. So in this example, so you would get back a tuple that just has P1 and U1, so it includes the givens in that tuple. and then the fact references for those two. Or for this one, you've got P1 and U1. It doesn't do anything for U2 because that's inside of an existential. So you've got P1 and U1 and the references for the user and the replicator at that level, but then a deeper level inside of the projection, you will have something that has P1, U1, and then U5. And so that way you can take a look at that subset of that user and that replicator, and you can say, okay, this environment goes along with that particular replicator. So those are kind of a way to join the results back up again. Okay, so that's what that returns, and so yeah, the composer, being the very last thing that that it calls, is the thing that puts those together. So you've got your result set tree, and you've got your fact records, and now we can actually get to composing. So let's kind of walk through this one because it's pretty important. So it first of all calls this compose internal, and then gets you back just the results of the very first result object. So basically, what you're looking for is an array of projected results, and this compose internal step will always give you back a collection of those results. So it's like, okay, I know that at the very top level of the tree there's only one root, and so yeah, this is just kind of collapsing that root back to a single return. But in general, that's not the case. So in general, we get back these child results. So a child results is that array of projected results, but also the parent fact IDs. And so these are the internal database IDs. These are only good inside of this particular composer. And where I just described how you can use this tuple of P1, U1, U5 from the outside to put things back together and which one belongs to which. Inside of the database, you've got something that's even easier to compare. You've got these IDs. So instead of those references, it's actually the fact IDs of those 2 or 3 or however many elements of the tuple. So that helps it to put things back together pretty quickly. So internally, you start by taking all of the rows, and so remember what the row looked like. The row was a collection of facts by index, and then their hash, fact ID, and data. So you take those, and then you just kind of turn them into what what the composer needs out of that information. So you find the identifier, you find the tuple, and you find the projection. So the identifier is pretty simple. That is just the fact IDs. In fact, it's just take those fact IDs for each row. That's your set of fact IDs. And so yeah, the identifier is an array of numbers, array of IDs, so that you can match it with the parent. And then the tuple, that gives you these fact references by name. So just go through all of your rows, and for each label in the query, so the label is the set of of all inputs and all outputs. So all the givens plus the labels of each of the different matches. Excuse me. So you just put those together, and now for each one, you grab the fact reference, the type, and the hash. So those two are pretty straightforward. And then the projection of is where it gets kind of interesting. So projection of takes the the actual row, and then turns it into the the JavaScript thing that you want the projection to actually mean. So we'll walk through this in a second, but before we do, let's kind of pop back out and see what it's going to be doing with all of these things. So it takes that set of fact IDs, the tuple, and the result JavaScript object, or just JavaScript value, whatever that particular projection was producing, and it gives you back a set of identified results. So so now it goes through this this kind of a I used to know a name for this algorithm, but it's basically where you go through two different lists at the same time, and then as soon as one of them switches to the next one, then you can make the next one switch as well. So this kind of zips the the child's results into the parent. But yeah, so we're going through each of the child result composers so that we can take its results and put them into the the right object inside of the parent. So so for each one, we find the result set of the same name. So the child result composers come from the specification, and the child result sets come from the execution of that SQL. So the result sets have the actual data in them, and the child result composer is just recursively another one of these things.
Yeah.
And so we find those, and then we call compose internal recursively. So it says, all right, now for that child's composer, go ahead and do this zip up thing that we're doing here at the parent level. So this is recursive in terms of the composer graph, not in terms of the result graph. So even as you get more and more results, you're still recursing just a small limited number of times based on the depth of the specification. So in the case of this particular specification, we're going to do this 3 times. Once for the top level, and then recursively for environments, and then recursively again for names, no matter how many results we get back. So so now let's pretend that we understand what compose internal does, because it's recursive and we're analyzing it right now. And so now it's got back a set of composed results. So these are the child results that have the tuple for each row and its fully realized JavaScript object. And that fully realized JavaScript object can now have child objects that are arrays of results, and it keeps going. And so then you add those to the results in each of your identified results. You go through and you add the matching child results into each of the parents. And So now this is where you do the group by, because at this point you still have, here's the list of all of the all the results, and you put the parent or the child result array into the parent. But now this is the thing that produces child result arrays for the next level up. So you go through each of your different child results, looking at the slice. Wait, no, not this slice. There's another one that does a subset comparison. Here you're just looking at the very first one, and you're saying, okay, give me just the first results. Oh no, this one is doing the subset. Okay, yeah. So give me the first result in that array, and then just slice off the length of the parent fact ID. Because remember, each one of these identifiers is an array of fact IDs. So so the child's identifier is going to be longer, and its prefix is going to be the parent ID. So so we just slice off the parent ID. That way we've got the IDs to compare against. So we do that just for the first one, and then we initialize the results to be just the tuple and the result for that first one. And this is where we go through the algorithm of now starting from the second one. You get its parent fact ID if it's equal. So you're comparing those two ID arrays. Then you go ahead and you add that to the list. Once you get to one that's not equal, you start a new list. So first of all, push that list of child results, and then it reinitialize. So now your parent fact IDs are this next parent fact IDs, and you start a brand new list of results with just one element in it. Keep on going, and then at the end, you're going to just have one set of results that you need to then push to that child results collection. And so this gives you an array of arrays, and each one is the group of results that belong to a single parent. So it kind of groups them together. So that's what that is doing in order to compose them. And now once you get back to the parent, that's where you're coming back out here. So you've already done that compose internal. You've got your composed results, and you're coming back out here, and you're finding, okay, for each array in here, let me see which parent that's supposed to go to. And then you just add that to that parent result before you group those together. And that is why up here, when you do that compose internal, you've got this array of arrays. But that array should contain just one group. They should all belong to the parent that is the set of givens. And so you just grab that one group and you give its results back. So I probably should have another check in here to just make sure that that's true. Just assert that you get back one group. If this algorithm is correct, then you always will. But I could have made a mistake. Okay. So any questions on how that composes before we now go into the projection?
It's complicated again.
Yeah.
But yeah, that's one of the parts I was stepping through. But I think with what we saw today, it will help.
Okay, good. Yeah. The goal here, even though the reason for the complexity is so that we can limit the number of round trips to the database, and have all the information that we need come back in one, one small constant number of result sets. So yeah, it's not doing a single round trip to get all of the results and then combining them together. Funny enough, Entity Framework used to do that. It used to give you back a sparse matrix of results, and then basically go through this algorithm to piece them together. And your list navigation properties, it would basically do this to populate those. But now Entity Framework does something more like this, where it does multiple result sets, and then stitches them together so that you don't get just one sparse result set that's got a lot of null values in the columns. But yeah, that is some complexity that you have to take in order to get some optimization. Okay, so now we are getting the projection of a particular row, and we're passing in these fact records that we fetched earlier. So we know that these are all of the fact records necessary to realize all of the facts that we are projecting. And so when we come in here, we've got different types of results that different types of projections that we can be running. We can be looking for a hash, a composite, a field, or a fact. So in fact, in this example, in this example right here, we're doing a hash, and we are doing a field, and here we're doing a composite. So the composite is I need environments and hash and identifier and names. And what was the last one? Oh, fact. Yeah, that's the most important one. So yeah, here we are. Yeah, that's value. That's value. In this case, we're not actually doing any fact projections. But if we were to project just U1 instead of the hash of U1 or U1.identifier, then we would get the fact projection. So if it's a field, then we just get the field value. Composite, we go through all of its elements, and we get the element value of each one of those. Hash, get the hash value. Fact, get the fact value. So those are the different things. The composite is the one that's the most complicated here, and this is because when you are sending in a projection from from the /read endpoint, it's very nice to be able to just give me all of the labels. And so if you just give it a specification with no projection, what it's actually going to parse into is a specification that has a composite that has no elements in it. So that's just kind of a shorthand way to represent that, I really just want all of the elements. And so it really should only be the human that's generating a specification like that. Any code that's running a specification shouldn't generate this, but it's handy for humans looking at the results.
Right.
So in that case, it's just giving you all the fields of all of the labels. But in the case that you do have some components in your composite, then it's going to give you the element value for each of those components. So let's walk through these one at a time. So we've got field, hash, fact, and element is going to be further down the page somewhere. So for the field, you already have the fields collection inside of the data. So you just get the label from the specification based on the name of the label in your projection. So inside of the projection, we've got the label U1, and then inside of the inside of this specification object, we've figured out what is the fact index for that label. So so that's our specification label. That way we can just look up that particular fact from the row and say we're looking for its fields and that particular field by name. So that's pretty straightforward. Hash value is also pretty straightforward. We're just getting the actual hash that we returned from that object. But then the fact value, this one is where we now take advantage of these fact records that we fetched. And so there's already a very useful method that's used all over the place in this code base to be able to hydrate a set of facts from a list of fact records. So here I'm saying I'm only interested in this one. Hydrate from fact tree could give you an entire array all at once. But in this case, I'm just interested in this one. So given these fact records, go ahead and recompose that particular fact. So now when you look at that fact, it's the JavaScript object that you would use in your code. So that would have the type and all of its fields and all of its predecessors, and they would all be fully realized, and it's ready to go. So yeah, by fetching all the fact records at once, that means that now as it's looping through each of the results, it's already got all the data it needs, so minimizing the round trips to the database. And then the last one is the element value. And so for this one, we've got, we're going through, basically this is a composite, so each element has a name, and so we're, and it has its own projection inside of that component. So we're doing, the field, the hash, the fact. The reason that we're not just recursively reusing this is that this component projection is not strictly the same set as the projection that we came up with, that we started with. And that's just because I don't support composites of composites. Okay. You can't put another composite inside of a component. I can't remember exactly why I don't support that, but if that is a thing that that you end up needing, there's another way to accomplish that. That is to do the projection where you get all of the components that you need, and then after that's in memory, you can then do another dot map in the case of JavaScript, or dot select in the case of .NET, in order to get it into the structure that you need. But at least at the time, I had a good reason for disallowing it. I might go back and allow it now that things have started to settle out. But at any rate, we've got our field hash and our fact. And so there's our hydrate from tree again. So this is where this particular projection type, so now this is a component projection. This projection type could be hash, field, fact, or specification. So the specification is when you have a child projection, like this right here, names or environments. That is a specification projection. And so a specification projection can only occur inside of a composite. It doesn't make sense for you to have, here at the top level, another specification. If that's what you wanted, you would just put that specification, you just combine it with the parent specification. So if it's a specification projection, then the way that that's actually going to be handled is that the result, or the result set tree is going to have a child with that particular name, and so the result composer is going to take that child and put that array into the parent. So this projection of doesn't need to handle that. And there's our little exhaustive check to make sure that we've handled every type of projection. So yeah, that gives you back the actual JavaScript type that that you're trying to select from that that particular projection. And that all rolls up into the projection of right here. So that ends up as the results inside of these identified results. That's the entire composer.
Yeah, no wonder that I've been suffering a little bit with that.
Yeah.
Another video that I'm gonna run next to the code while stepping through.
Yeah, it's a complex one, but yeah, solves the problem.
Look, sometimes that's the only way to make it efficient.
Yep.
If you have too many round trips to get the data.
Yeah, very true. Okay, now let's see if... All right, yeah, that's not too bad. Okay, I'm just playing around with the the recording settings. Yeah, this is gonna, definitely need to see if we can get that fixed for next time. But
because when I logged into Discord, normally it gives you the book lab with video, and in the beginning he only said voice channel or something strange.
Okay. Yeah, I always remember it being called a voice channel, even though it supports video.
There were some updates. There were some updates when I started.
Yeah.
That might be the cause.
Yeah. Yeah, and so I think what you'll see when you rewatch the video, see what I saw on my side is that whenever I switched over to the other window and it was on top of Discord, it blanked out the videos, and that didn't used to happen. So I think they're doing their own optimization. It's like, oh well, if you can't see the videos, then let's not update those parts of the window.
Yeah.
But I've actually got Discord, or not. I've got OBS set up to take that window, even though it's behind another one, and take those parts and put them into compose them into the output stream, and then I just got black rectangles.
So you still have the separate image streams or the different window contents saved separately.
OBS does that composition before it saves, so I don't have separate outputs. But yeah, that way I could have Discord running on the monitor that has the camera, and then all of my like Visual Studio Code in this case running on the monitor that has the camera, and I can just put that on top, which is why you see the infinite video before I do that. But yeah, they're not supporting that now. So actually right now I've got Discord running on my other monitor, so that it's not occluded by any other windows, and so it's picking it up. But because this other monitor is a different resolution, it's not the preset size. So I'm resizing this window, and that's trying to line things up, and it's not perfect, but
we will see the result.
yeah. All right. Well,
All
hopefully
right.
that will help with the next step.
And the distribution rules, that was for next time then.
Yes, yeah, I've actually been trying to get to distribution rules for a little while now, and it's like, no, this is more important. Let's talk about that. But next time let's talk about distribution rules. Unless I have something more important to talk about, which, as I'm thinking about it, I probably will. So I'm very close to being able to deploy the multi-tenant replicator. So I think actually maybe next time it'll be all about the multi-tenant replicator.
Okay. Let's see. You are like obsessed now by the replicator.
Yes, indeed. Yeah, this is how it gets out to other people, and it's accessible.
So, if you have a replicator which is easy integratable, I think that's a very nice step forward.
Yeah. Yeah, and then I need to do those Groundhog Day type of videos again. But yeah, this time it'll be, let's go up to dev.janaka.com, create a replicator, put it here. Then create React app. Here's a whole thing. All right, next episode, do React Native. Here's a whole thing. Yeah, if I can get to a full app in an hour.
Start up your replicator, get to your Google Sheets, and build an application.
Yeah, there you go. Yeah, Google Sheets, or here you go, screen scraping, there you go.
Yeah, and when everything works, then Google decides to stop Google Sheets.
Yeah.
No. Okay, I'm gonna go back to a little bit more Google Sheets, finish that, and then go back to historical modeling, because I'm a little bit behind with historical modeling.
Sounds good. Well, good luck to you.
Michael, thank you very much, and see you next week, Thursday.
Indeed. See you then.
Okay. Bye-bye.
Bye.